Hi and welcome to Unit 1 Topic 2 Video 12, and in this video we're going to look at some examples of force situations involving vectors. So let's look at our first example, the second in this video series. An object is subjected to a force of F newtons. So be careful there, in your exam situation it would be clearer that one is F and the other is a unit. At an incline of 10 degrees, if the horizontal component of this force is 25 newtons, what is the magnitude of the force? Okay, so let's start by denoting our object. We're going to use just a point, and there it is there, and it's being subjected to a force of F newtons. Now, at an incline of 10 degrees, so there's our 10 degrees, and we're told that the horizontal component, because we can break it into components, is 25 newtons. We want to know what the magnitude of the force is. So basically we just want to know what F equals, and we don't care about direction. The magnitude doesn't really matter about the direction. So this is fully interpretation. We know the I component. We've got F2 as the J component, but we don't have to do a lot of work to recognise that we've got a really easy right angle triangle situation here. So cos, because we're dealing with adjacent, cos of 10 is equal to adjacent 25 over F, the horizontal. So if we wanted to work out F2, we'd use tan, but we're going to work out F, our magnitude of our overall force, and so therefore F will equal 25 over cos of 10, and 25 over cos of 10 works out to be 25.38. Now that's a pretty small angle, so we're expecting it to be just a little bit more than 25, and it's 25.38 newtons. So that's where we wanted to go. Now, on our next example, I just want to make a note here, and you can have a read of this. The textbook we use doesn't really consider gravity at Unit 1. So it will state that a 10 kilogram object has weight 10 kg Wt, where Wt represents gravity. So it's a shortened version of weight, essentially. So it's good because it's easy to transfer different locations with different gravities, so that's handy. But it's not a nice way to represent other forces, and it doesn't really help you understand G. So we'll move forward with this. I'm going to use this a lot in these videos because of what you'll be looking at in that textbook. But just keep in mind that as we move into Unit 3, we're going to probably drop that and start considering gravity as negative 9.8 or negative 10, if that's what's provided to you in the question. So let's have a look at example 3. An object being acted on by three forces is in equilibrium. So equilibrium, you recall, that means that it's not moving. Calculate the horizontal component of F3. Okay, so we've got F3 there, and we want to calculate the horizontal component. So that is this length here. Now, that means we want to calculate the I component. So I'll just pop a little thing here. Now, it's important to put this everywhere because we don't always go this way. It's important to denote that in this case we're going I and J like that. And we want to calculate the I component. We know it's in equilibrium, so that means that we can set up our force equation for the I component. But what I'm going to do, I'm going to go a little bit too far and just do a little bit more than we need, just to show you what it looks like. And then we'll break it down and solve it. Okay, so the overall resultant force is this. We've got our I components, and keep in mind, and I'll do it as an example here, that the I component of this one is cos 25 equals the F1 I component over 40, which means that F1I is equal to 40 cos 25. So that's important to recognise here as we build it forward. Now the thing with the F3 is that we don't know the value of the angle, and so that's going to cause us some problems moving forward. So we're going to have to use both components, but we wouldn't have to do this whole equation I'm about to do now. You could break it into two parts early, but let's do the whole equation anyway. The resultant force looks like this. It looks like 40 cos 25, so that's this part, plus 30 cos 55, so that's this part, and the plus should actually be a minus because it's in this direction, And keep in mind in an earlier lesson, if we didn't have 55, if we actually used that angle, we wouldn't have to worry about the minuses. And then minus F3 cos theta. And that's theta. We don't know theta. Okay, that's our I component. And then our J component is this. F1 is 40 sine 25 plus 30 sine 55. So this is a plus. They're both in a positive direction. But then minus F3 sine theta J equals 0I plus 0J, or just 0. So that's our component form. What we can do with this is we can equate the components. So that, what I'm saying there is, I mean the I component is equal to the I component here, and the J component is equal to the J component here. So this single equation actually gives us two equations, two pieces of information. We can't add something to the I and make the object move vertically. That only happens in a J. So let's start with equation 1, which is 40 cos 25. I could work this in a calculator, but I really don't want to because then I have to round. 5 minus F3 cos theta equals 0. And therefore, I'll do a little bit in one go here. F3 cos theta is equal to 40 cos 25 minus 30 cos 55. And don't worry, the negatives and positives are correct. And equation 2, for the same reason, I'm just going to skip to it. It's F3 sine theta equals 40 sine 25 plus 30 sine 55. Now here's something you will have covered, or you'll be very soon covering in methods. So I'm going to tell it to you. And that thing is that for this question it's important to recognise that sine theta over cos theta equals tan theta. Because I've got a problem here with solving for theta or F3. But what I'm going to do is I'm going to do equation 1 divided by equation 2. So that will look like this. And I wouldn't have set it out like this. I'd probably write it on a new line. But that's going to look like this. There. Which is going to cancel out the F3s. So I'm going to end up with cos theta over sine theta is equal to this stuff. 40 cos 25 minus 30 cos 55 over 40 sine 25 minus plus 30 sine 55. And that means that that stuff, which I don't want to write out again, so I'm going to be really cheeky and just say that's equal to tan theta. And then, I won't be cheeky this time, but I will write out that we know the angle we do is tan inverse. So theta is equal to 65.34 degrees. I'll keep that value in my calculator, but it's important to recognise that we know the value from this. The other thing we could do is keep our exact value. Now that I know theta though, I get F3 sine theta is equal to 40 sine 25 plus 30 sine 55. And keep in mind, I could, if I wanted to, I could use the other equation, F3 cos theta, but I've used this one and it doesn't really matter. And F3 is equal to 40 sine 25 plus 30 sine 55 divided by sine 65.34, which hopefully I've kept in my calculator, and that comes out at 45.64 newtons. So it's important to see here in the first question, when we first started this question, we recognise we don't know the magnitude or the direction of this vector, but because it's in I and J components, we have two unknowns, but we also have two relationships to the vertical and the horizontal that have to equal 0. So we've got enough information, we've used that information, and there's our solution. Now here's version 2, which you'll be looking at this going, oh no, not another one. Oops, sorry. But I want to just point out that things can change as well. So that was vectors in polar form, keeping the numbers nice by using the polar form. This is vectors in component form. An object acted on by three forces is in equilibrium. So we've got that word equilibrium again. Given that F1 equals that and F2 equals that, calculate the horizontal component of F3. So this is interesting. Oh, actually, we didn't finish this question. We're going to calculate the horizontal component. So the horizontal component, which is F3I, will be equal to 45.64 times sine 65.34. And that's equal to 41.48 newtons. That's the horizontal component. So don't forget your chickens. Always remember to go back and reread the question and do what it's actually asking. So here we are. Again, calculate the horizontal component. So we'll make sure that we do it this time. So we're going to calculate the resultant force. So first, we don't know direction, we don't know force, but we do know this. There's my central point, and force 1 is 3 plus 5, which is about there. And force 2 is 2 minus 1, oops, that's wrong, which is about there. And force 3 is something that makes it in equilibrium, so it's probably going to be like that. So I'm expecting it about there, whatever that is. But notice here that force 1 plus force 2 plus force 3 equals 0, which means that 3i plus 5j plus 2i minus j plus, I don't know, ai plus bj equals 0. And that means 3 plus 2 is 5 plus ai plus 2 minus 1, 5 minus 1 is 4. 4 plus bj equals 0. And that means that a equals negative 5 and b equals negative 4. So this must be 0 and this must be 0. It's the only way that can happen. And so now we've got our overall. And our overall is F3 is negative 5i, and not even a plus, minus 4j. And then we want the horizontal component. Well, there it is. It's the I component. So the horizontal component of F3 is horizontal component equals negative 5. Job done. So it's a little bit easier again in component form. You'll see this with vectors all the time. Basically, some things are great in polar form, some things are great in component form. It's not usually great in both forms. So there we have that example though, and that is the end of video 12. All the best.